Here's Classwork 6, Standard Deviation. Now I'm going to go straight through, but I'll pause a little bit between each problem so that you can pause the video and reflect and have a chance to write down your thoughts. So our overview, we'll talk about summarizing spread with standard deviation by talking about two different cities, and then I'll have you think critically about standard deviation. So a quick review, what are the three ways of characterizing or describing a distribution? We've mentioned these a couple of times at this point, but just to recap, when we're describing a distribution, typically we talk about the shape, the center, and the spread of that distribution. So the shape would be things like looking at the histogram, looking for outliers. Is it skewed? Is it normal? The center, we are typically looking at the mean. And then with spread, most of the time we're looking at standard deviation. And so today we'll be looking at sort of what is that concept of standard deviation? What does it mean? And how do we sort of build that concept? So summarizing spread with standard deviation. Take a look at these distributions of temperatures below. The table and the dot plots both show you the same distributions. There's a distribution for St. Louis, and there's one for San Francisco. They show the temperatures for all 12 months, so monthly normal temperature, so I'm guessing that this must be the average temperature for the month. For all 12 months for, again, St. Louis, as you can see on the top row of the table, San Francisco on the bottom row of the table. Same information is presented in the dot plot. So St. Louis, the temperatures are shown on the top part of the dot plot. San Francisco, the temperatures are represented on the bottom part of the dot plot. So take a moment, pause, review in your workbook, just observe. And then by looking at the dot plot only, so without getting a calculator out, without calculating anything, what I want you to do is just by eyeballing, just by looking at that dot plot, try to select a single temperature value that you feel represents the typical normal temperature for St. Louis. So looking at these temperatures in the top row, just eyeballing it, try to identify one temperature that you would choose to represent sort of the typical St. Louis normal temperature. Once you've done that, I want you to do the same thing with San Francisco. Look at those San Francisco temperatures, and just by eyeballing it, not calculating anything, try to find a temperature that you feel sort of represents the typical normal temperature in San Francisco. Once you've identified your two temperatures, I want you to think about them and look at them. Are they close in value? A lot of people here will typically choose somewhere kind of in the middle for both of these distributions. Typically around, I don't know, 56, 57, 58 for both of these. Sometimes with St. Louis, people will choose down here because there's more than one, because that's where the mode is. Sometimes they'll choose something quite different. So if you chose something quite different, that is not a wrong answer. The thing is, there are a lot of sort of different options here, right? So typically people choose close together on San Francisco, may see a little more variety in St. Louis, but often people find that the typical temperature they choose sort of not that different for these two cities. So suppose that you have a friend who's going to move to San Francisco. The only piece of information your friend has about the weather in San Francisco is that the mean or average temperature is 57 degrees. So for all of these 12 months of the year, the average temperature for San Francisco is 57 degrees. Do you think your friend will be able to pack clothes that are appropriate for the weather? Now let's say your friend was moving to St. Louis in January, and the only information that she knows about the weather is that the average temperature for St. Louis for the year is 56 degrees. Do you think your friend will be able to pack clothes that are appropriate for the weather? Again, make sure you're pausing to reflect, think on these, put your thoughts down. And then think about your answers to numbers 2 and 3. What do those answers tell you about the representative temperatures for those two cities? What I mean by that is, okay, so we see that the mean temperature for San Francisco is 57. The mean temperature for St. Louis was 56. In both of these cases, this mean is supposed to characterize the center of this distribution. It's supposed to represent the distribution. So, do you think that she'd be able to pack appropriately given this information? Would she be able to pack appropriately given this information? And then, what does that tell you about how well this average represents the city of San Francisco's temperatures in general? And what does it tell you about how well this average represents the temperatures in St. Louis in general? Then I want you to go ahead and re-examine these dot plots. Look at them again. Think about your answers to 2, 3, and 4. And then try to write a sentence describing how variable or how spread out, how many differences you see in the monthly normal temperature values for the two different cities. So when I say variable, again, I'm just talking about differences. Vary, something that varies. So looking at this dot plot, how would you describe how much the temperatures for St. Louis vary compared to how much the temperatures for San Francisco vary? Try to write a sentence that compares those two. Now, one measure of variability that we look at when we're talking about just individual data values is called a deviation. And a deviation is literally just a distance from the mean. So if you imagine, if you have, this is the mean, and here's some data point. If you took a little measuring tape and measured how far away is that data point X from that mean, that difference between them is the deviation. So you can have a deviation that's positive when X is higher than the mean. You can have a deviation that's negative when X is lower than the mean. So the deviation is just the difference between any given point that we're talking about and the mean for the data set. So here I've split the tables into two for each city. And then I've also added a second row to each table showing the deviations for each month. So the deviations are calculated using the formula that's shown here. So deviation is equal to the data value minus the mean. So in other words, X, any data value from your data set, minus X bar, the mean of your sample. Below we can see the deviations from the mean for almost every month in St. Louis and San Francisco. So you'll see that I strategically left January blank for St. Louis. So if you want to check this, we can always pull out a calculator. Okay, I think I'm back. So, for example, looking at February, we would take the data point 34, that would be our X, minus the mean. And if you remember from above, the mean for St. Louis was 56, I believe. And we get negative 22. So that's where these deviations are coming from. 45 minus the mean of 56 and we get a deviation or a difference of -11. It's negative because our data point is below the mean. For April, we can see our data point is above the mean by 1, so our deviation is +1. We're 1 above the mean. Here we're 10 above the mean, 19 above the mean, 24 above the mean, and so on. So take a moment and calculate the deviation for January in St. Louis. Go ahead and pause and calculate, and then I'll do the same. So hopefully you got -27. So let me try to get rid of that calculator. There we go. Okay, so that is for looking at individual data points, right? If we're interested in just one data point, we want to know how far away is it from the mean, cool. But what if we're talking about a data set that has like thousands of data points? You don't want to talk about how far is each and every single data point away from the mean. That's not particularly helpful. What we really want is some sort of measurement that's going to tell us sort of like generally how spread out are the data. Are they pretty close together? Are they pretty far apart? So one approach we may take to measuring that variability is to calculate the average deviation, right? So if we have all these deviations saying how far away those points are from the mean, then why don't we just figure out how far away are they on average, right? Kind of makes sense. We want to know sort of on average how spread out is it. Find the average of the deviations. So that is what I would like you to do. I want you to pause the video after I explain and pull out a calculator and compute the average deviation for St. Louis. So in other words, I want you to compute the mean for these bottom deviation values. And remember, how do we compute the mean? By adding up all of those values and then dividing by how many we just added up. So since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 months in the year, we are going to add up all 12 of these values and divide by 12. So you go ahead and get your calculator while I get mine back up. All right, so I'm going to do plus 22 minus. And I get, okay, I added them all up and I get 0 divided by 12 is 0. You may have done this a couple times because 0 seems like a weird answer, right? We can see that there's variation here. There's not 0 variation. So can't be the right answer, right? It actually is the right answer. The answer is 0. So let me get rid of that. So notice that the sum of the deviations is 0. This is true for every data set. The sum of the deviations is 0 because the mean is the point where all of the deviations balance out on both sides of the mean. That's what the mean does. It's balancing all of the deviations on both sides. So you may remember we talked about this small data set, 5, 5, 5, 10, 20. Probably should have put those in there. And we talked about how, well, you can consider 5 to be the middle because it's literally in the middle position. Or you can consider 9 to be the middle, because 9 is the point where all these values balance. They balance because 5 is 4 below, 4 below, 4 below, and then on the other side, right, giving us a total of 12 below. Then on this side, we have 1 above and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 above, giving us a total of 12 negatives, 12 negative deviations, and 12 positive deviations. This is the mean's job. It is the whole job of the mean is to balance the negatives with the positives. So that means every time we add up all these deviations, all the negatives are going to balance out all the positives, and it will always be 0. So that's not going to work, right? If it's always 0, I mean, would we expect, looking at these dot plots, would you expect these to have the same, both to have 0 sort of average deviation? No. So, intuitively, which of those cities do you suspect should have a bigger average deviation? So again, it may help to look back at your dot plots. Which one of these do you suspect should intuitively have a bigger average deviation? Hopefully you said St. Louis. Because it's more spread out, right? If it's more spread out, then that means we have more deviations, more things that are far away from that mean, that center point. Now, we could do two things to try to keep these deviations from canceling each other out like we see here. One, we could take the absolute value of everything first, which means that we would just say, well, instead of -4, let's make this +4. Instead of -4, we'll say it's +4. Instead of negative, it's +4. And just make all the negatives into positives. We could do that, theoretically. Or we could square all those negatives and then later just take the square root to undo that. Because when you square a negative number, it becomes positive. And then you take the square root of that and now it's positive. So I won't go into all the gory details of why we will do method number 2, partly because I don't know exactly why we don't do number 1. But I do know that as far as I know is that because when we go to use the standard deviation and variability in some of the statistical analyses that we're going to use in the future in inferential testing when we get there, those don't work algebraically if you just change all the signs, if you just willy-nilly change negatives to positives using absolute value. So my understanding is that's why we don't do that. Conceptually, this makes a lot more sense. And so for new statistician students, it probably makes a lot less sense, but stick with me here. So here is our table like we had before. We have, for St. Louis, the month, the temperature, the deviation, and now I've added another line, deviation squared. So all I've done is I've literally taken the deviation and I've squared it and put that value right there. So unfortunately, I think I lost my calculator. Here we go. So if we take this 27 negative and we square it, we get positive 729. So that's where all these numbers are coming from. Negative 22 squared, 484. Negative 11 squared, 121. 1 squared, 1. 10 squared, 100, and so on. So go ahead, take a moment. Let's fill in December. So I want you to feel like you're doing something too here, right? Let's take a moment, fill in December. What is negative 22 squared? Hopefully you got 484. If you were looking over here, you could have seen that answer was already over there. So now, if you would like to, you can add all these numbers up, but I've already done it ahead of time, and I can tell you that if you add all those numbers up, all of these squared deviations, because literally all I've done is squared each of the deviations. If you add up all the squared deviations, then you will get 3,640. So if you add these all up, you get 3,640. And this number is called the sum of squares. And you will see it abbreviated SS. So why is it called the sum of squares? Well, we've squared all of these deviations, and then we sum them all up, just add them all up. So we sum all the squared deviations. That's our sum of squares. Now, if we take this sum of squares, so I'm just going to sort of reinterpret, I'm going to connect a little bit with our formula. So what we've done so far is we've said, okay, for each data point, subtract the mean, and that's my deviation. Now, if I try to find the average deviation, it's always 0. That's not going to work. So to get around that, I'm going to square all my deviations so that they become positive. Great. Then, once I have all of my square deviations, I am going to add them all up. I'm going to sum the squared deviations. Okay, so this part of that equation is the sum of squares. Now, if we then divide that number, keep in mind this is, for this problem, 3,640. If we divided that by n, the number of numbers that we just added up, I want you to think about this. We're adding up a bunch of numbers and then dividing by how many numbers we just added up. I'm hoping that sounds a little familiar. We added up a bunch of numbers and then we divided by how many numbers we added up. Okay, so what we're doing is we're sort of finding an average here, and we'll talk about what that is. But what this is called, this number that we get, it's called the variance. Now, the variance is an important way of summarizing how spread out a distribution is. This is one of the measurements that we typically use. The sample variance is denoted by S squared. So this thing, if we're talking about for a sample, we would denote the sample variance as S squared. If we're talking about population variance, then we use a different symbol for that. We use sigma, little sigma squared. It's like a little O with a little extra hat kind of thing on it. So sigma squared. So let's think about why don't we use that here? So what are these numbers that we're adding up? So think back, these are temperatures from St. Louis from all year round. Average typical temperatures, average normal highs, I guess. So think about these temperatures. There are 12 temperatures that we have. Are these all of the temperatures for the whole entire year in St. Louis? Did they only have these 12 temperatures all year? That's it? Or are these selected temperatures from the year, right? So if we were talking about every single temperature that they had, then that would be the population. We would use sigma squared. But really, this is just a sample. We're saying, okay, average, find the average high for each of these months, and then now we've got 12 data points. And so those 12 data points, that is our sample of data. So we are actually going to be computing the sample variance, and then from there, the sample standard deviation. You may be wondering, why are we even bothering differentiating between sample and population at this point? And so we're going to have to clarify that in a moment. Okay, let me send this away. Okay. Now, since we're calculating S squared, the sample variance, we're going to divide the number from number 10, that 3640, by n minus 1, not n. Why? What does this do? Now, this is a totally weird concept. I will fully admit that. So, we're talking about S squared and sigma squared. And I'm just going to rewrite out these two equations. So we've got, just from above, you sum all the squared deviations and divide by something. So this is saying, since we're calculating S squared, we divide that number by n minus 1. So down here we do n minus 1. Versus here, we would do n. Why? So this is a strange idea. So bear with me a little bit. So this is for the population, the whole population, everybody. This is for the sample. Now I want you to think about population and sample. Which one's bigger? The population is bigger, right? Population is everybody in your population. Your sample is a smaller chunk of your population, right? It's not necessarily all together like this. It's sort of from here and from there, but it's a piece of your population. It's a slice of the pie is your sample. Now think about if this is a ton of different people, and this is also different people, but fewer different people, where would you expect to see more variation? In this larger group with more people, or in this smaller group with fewer people? Where would you expect to see more differences? So hopefully you recognize that when there's more people, we're probably going to see more variation. There's more chances that we're going to see more differences among people if there's more people. So that means that we typically get higher variation in the population than in the sample. Now, this is going to sort of depend. Is the sample this big or is the sample this big? Right? If your sample is really big, then the difference is not going to be that different between them. But if your sample is really tiny, then maybe it is going to be a big difference. Let's go back to our original. So keep in mind, when we're looking at these sample statistics, we're always trying to sort of estimate for the whole population, right? We don't just care about the sample. We care about the sample because we're trying to figure out something about the whole population. We're trying to infer something about the population. So we're trying to estimate the variability that we see in the big population based on the variability we see in the smaller sample. We know, based on research and and all sorts of, I don't know, smart people stuff, that this tends to be a little small in terms of variation compared to this. So somebody figured out the relationship between how many people are in your sample and how much we sort of need to like adjust the numbers a little bit to make up for the fact that the population tends to have a little bit more variability, right? We know that the sample tends to have a little bit smaller variability. Since we're trying to estimate for the whole population, we want to bump it up a little bit. How much do we bump it up? Well, it sort of depends on how many people were in our sample. If we had a really small sample, we're going to need to sort of bump it up a little more. If we had a pretty good sized sample, we don't really need to bump it up that much. So this n minus 1 versus this n, that is like our fudging factor that we're using to sort of be like, well, this one's probably a little bit too small, so divide by something just a little bit smaller to make the overall thing a little bit bigger. Right? So to illustrate this idea, let's say if n was 5, then we would divide by whatever's on top. If we're talking about the whole population, we'd divide by 5. Talking about here, it would be divide by 4. Now think about which one's bigger. The one divided by n or the one divided by n minus 1? Hopefully, you see that this one's a little bit bigger than this one. When you divide by something smaller, the overall result is a little bit bigger. Now, if we were talking about 100, and this is 99, well, now the difference between 1 over 100 and 1 over 99 is pretty small, right? And if we added another one there, that's even smaller. So the higher our n is, the less this really matters, right? The less this is going to affect things. But if we have a really small n, like 3, this is going to make a big difference between 1/3 and 1/2, right? 33% and 50%, basically. So when you have a small sample size, this difference matters more. When you have a bigger sample size, they're not that different. But again, why do we do this? Well, it's because we're trying to account for the fact that the sample is going to be just a little bit too small. And so we adjust the formula to make it just a little bit bigger to be a better representation of the whole population. So I encourage you, pause for a moment, digest, write down your thoughts, and then we'll keep going. Oops. All right. So we were talking about, no, I don't want to draw with touch. Thank you. So we were talking about sample variance and population variance. In this case, since we're working with a sample, we're using this one. So here again is the formula for the sample variance. S squared is the sum of the squared deviations divided by n minus 1. Note that n represents the sample size, or the number of data points in your distribution, which in this case is equal to 12 for each city, since we're talking about 12 different months. So for St. Louis, the sample variance is, if we were to add up all those square deviations, like I said, it adds to 3,640. That goes on top. On bottom is 12 minus 1 is 11. If you divide that out, we get about 331. For San Francisco, if you calculate the sample variance, if you add up that bottom row of the squared deviations, wherever it is, way over, I guess you would have to square them all first and do it yourself, or you can take my word for it. And believe me when I say that it is 150. So if you square all the deviations and add them up, 150, divide by 12 minus 1, because again, this is also a sample, and we get about 13.6. Now, I want you to pause and think. If I told you the sample variance for temperatures in St. Louis is about 331 for the year, is that going to help you pack better? Or is it going to help your friend who's moving there in January? Is that going to help them pack better, knowing that the sample variance is 331? Does that make sense in terms of temperature? And hopefully you realize, no, it sort of doesn't make any sense. Right? And why doesn't this make sense? Because we squared all the numbers. Now, when we squared all those numbers, not only did we get rid of the negatives, yay, but we also made those numbers really, really big. And we don't want them to be really, really big. We want them to be normal temperatures so we can interpret them the way we would regular temperatures, so we can actually use them for something. So this means we're one step short of where we want to be. The variance is really an average of those squared deviations, right? You square all those deviations, add them up, and divide by n, or n minus 1. But we don't really want the average squared deviation. What we're trying to basically represent is the average regular deviation, not squared. So what can we do if we want to turn it back into an average of the deviations? How do we undo that square that we did? We're going to take the square root, right? This guy. Now, when we take the square root of the variance, right? So if you take the square root of the variance, that is called standard deviation. If you are worried because this is very complicated, you will not have to do any of this by hand in this class. I can't guarantee for other classes. What I am really concerned with is, again, the concept, that you sort of get the concept behind it. Okay, so when we take the square root of the variance, it's called the standard deviation and is denoted as s, right? So if you take the square root of s squared, which is what we were talking about, s is the standard deviation. So what I would like you to do is, again, to pause and calculate the standard deviation for the temperatures in St. Louis and San Francisco using what you have right here. So if we take the square root of this variance, that will tell us the standard deviation for St. Louis. And if we take the square root of this one, that will tell us the standard deviation for San Francisco. All right, so I'm going to do 330.9.91 and then square root that. Is that right? That doesn't seem right. Is that the right button? 330.9. Oh, what did I just do? I guess maybe that is right. 8.19. Okay, let's do San Francisco, 13.64 square root. It's like, that looks right. Okay. Oh, I wonder if maybe I did the same thing. Okay, I'm gonna do this one again and make sure. Ha! Okay, that looks right. Thanks for sticking with me, guys and gals and other. Okay, let's go back. Here we go. Okay, calculator, I guess you can just stay up there. Okay, so the standard deviation for St. Louis 18.19, and then for San Francisco 3.69. So let's write a sentence interpreting the variability of monthly average temperatures in St. Louis and San Francisco using the standard deviation for each city. So I'll go ahead and do one for St. Louis, and then you can go ahead and keep going for San Francisco. So, for example, before when we compared St. Louis and San Francisco, we indicated that intuitively we thought that it should be higher for St. Louis, which we see in this case it is. So I might say something like the monthly average temperatures in St. Louis vary by about 18.2 degrees on average. Right? So, like, on average throughout the year, the temperatures vary by about 18 and a little bit degrees. So, go ahead and do the same for San Francisco. Once you've had a chance to do that, then take a look at the deviations for each city again. So, looking at the deviations. Remember how we tried to average them, right? Find the average of these, and we couldn't do it because of the negatives canceling out all the positives? Well, just eyeballing these numbers, do these seem like they sort of fit the bill, right? About 18, does that seem like it could be sort of the average of these absolute numbers? And then 3.69, does that look like a reasonable sort of average distance for these numbers? And then the last few things I want you to think about. So let's think about what standard deviation tells us about the distribution. So recall that the standard deviation is roughly, conceptually, approximately, an average of the deviations from the mean. Right? So if we have some distribution, here's the mean. It's kind of crooked, sorry. And their data points, spread out on either side, and we sort of figure out, well, sort of how far away are they on average? What's that average distance? So in some sense, the standard deviation gives the average distance of the data values from that sample mean, assuming it's more accurate. Now consider the standard deviation of St. Louis, which was 18 point rounding. So what is the interpretation of that number? So we might say something like, on average, the temperatures in St. Louis deviate from the mean or differ from the mean or vary from the mean by about approximately 18 degrees. Right? That's essentially what we're saying is that throughout the year, if we look at these temperatures, how much they vary sort of on average from that mean is about 18 degrees. So if you think about this concept, what I really want you to take away here is this idea that what does the standard deviation tell us? It really is telling us sort of the average distance from the mean, or the average spread, right? The average, how far away is all the data from the mean? If it's a very small standard deviation, like we see here with San Francisco, where it was 3.69, this represents the case where the data is all fairly close together. Remember in the dot plot. Here, where this number is much higher, this represents where the data are much more spread apart. So a high standard deviation means our data are much more spread apart. A low standard deviation means they're more clustered together. And then finally, some questions to think about. So, could the standard deviation of a data set ever be negative? And I really want you to think about this one and just kind of come up with your thoughts. And then at the beginning of the next class, we'll talk through these. Could the standard deviation ever be zero? Is there ever a case, thinking about what standard deviation is conceptually, the average distance, could it ever be negative? Could it ever be zero? If yes, how? And then this question, which generally appears on some tests sometime in my class, how are the concepts of mean and standard deviation similar? What about them is similar? Thinking about the mean as that sort of balancing point, it's kind of averaging something. Standard deviation, finding that measure of spread, but again, it's kind of has to do with averaging something. So I encourage you to think about this idea of averages, but then what are they measuring? What are they averaging? All right, so think about those and then write down your thoughts, and we will discuss at the beginning of next class. So thanks very much. I know this is a very difficult concept. I will post some extra resources to help understand a little better, and I will see you soon. Thanks.